Each child in a first grade class is given a green, red, yellow, and brown crayons, and some will use some, and will use some or all of them to color a circle which has been divided into 4 equal parts. Already I'm getting sort of a picture in my head. Okay, circle divided into 4 equal parts. And oh, look at that, I've got some colors on the side here. So red, yellow, and oh, I don't have a brown. I'll just use purple. Okay. Anyway, teacher has instructed the student to leave no part uncolored, okay, but that any one part must be entirely the same color. So basically what I've drawn here without even realizing it. Okay, now specifically somebody was asking about C and D. Let's jump into them and see if we do. George doesn't like the color red, so he definitely won't use that crayon. In how many different ways can George color the circle using one or more of the other colors? Interesting. And just while we're here reading D part, in how many ways can a child who isn't George color the circle? Well, that's interesting. So I would probably break this down into, again, sort of a series of choices. Okay. Choosing how many colors you're going to use. Now that might not necessarily be the best way or only way to do the question, but that's how I would view the counting problem here. Okay. So I'll start with George here. George doesn't like the color red. Okay, so again, I like drawing a little picture, just imagining things. So George, so no red. Okay. Now there aren't any other restrictions here that I can see. Okay, so it's entirely possible that we could use green for the whole thing, right? Or we could use yellows for the whole thing, or just a combination of yellows and greens. All we know is George is going to use one or more of the other colors. So George has 3 colors to pick from. Okay. So what could we do? Well, we could have a situation where George uses exactly one color. In which case the circle I get is going to all be green, or all be yellow, or all be brown. Right. So there really isn't a choice for where the colors go, because it's all going to be the same color, but we have a choice of 3 colors to pick from. So there's 3 ways for George to use exactly one color. What if George uses exactly 2 colors? Okay. So using exactly 2 colors, what could we do? Well, first he's got to choose the 2 of the 3 colors that he's going to use. Right? And so just like before, it's easier to just say, I'm going to pick the one color that George doesn't use. Okay. But now he's got to use those 2. It's got to be exactly 2 colors that he uses. Now there's, I think it's 4. It was 4. I keep drawing 4, right? But, yeah, a circle that's been divided into 4 equal parts. Okay. So now the challenge here is, well, how many ways are there for him to start coloring using his 2 colors? You know, he could use one of the colors 3 times, and then the other color only once. Right? That's possible. How many ways are there for him to do that? And we're breaking the problem down a little bit further. So he could use one color for 3 of the sections and the other color once. How many ways are there to do that? Well, if he's chosen his colors, okay, he really doesn't have any choice. He's got to pick 3 of them that are side by side, and then one other one gets the second color. So there's just 2 choices here. Okay, 2 choices. Which of the 2 colors he's picked is only used for one section. Okay. So, or I'm actually going to write this up a bit nicer. So here's our case, exactly 2 used. Okay. So 3 ways to pick his colors. Okay. And now I'm getting even more cases. So three the same and 1 different. And so for that way, there's two ways to do that. There's two ways to use 3. Now you might say, well, hold on, what if he does something like this? Aren't those different? No, that's where the circle comes in. Yeah, that's what we've learned in sort of a rotational symmetry sort of thing. These are the same ways of coloring the circle, because the circle doesn't really have a top or a bottom or anything like that. So there's only 2 ways for him to do that. Just pick which color. Is it green that is left out and we use a bunch of yellow? Or do we use a bunch of green and yellow is only used once? So that's one case. Okay. Or we could have 2 colors and 2 colors. Now how many ways are there for him to do 2 colors and 2 colors? Well, there's 2 possibilities. Either the same colors are opposite each other, or the same colors are beside each other. Well, that's it. So there's 2 ways of doing that. Okay. So this OR tells me to add these up. 2 ways of doing that, 2 ways of doing that. So 4 ways to color. Okay. Times the 3 ways. So first I pick my color, then I actually color things in. So 12 ways to color overall for having exactly 2 of the colors used. And again, I'll remind you, there were 3 ways to color George's circle when exactly 1 color was used. Okay? But we have one other possibility. He uses all 3 of his colors, because he can't use red, but he can use green and yellow and brown. So how many ways are there to do that? Well, he doesn't have a choice of which colors he uses, because he has to use all of them. So there's only one way to pick all the colors. Don't bother saying that. But how many ways can he actually color things in now? Okay. So, well, think about it. We've got, what cases could we possibly have? So if I'm using 3 colors, let's just pretend to be George for a moment. I got orange, and maybe I use a green. I don't have a brown, so I'm just using random colors here. But each color has to be used at least once, right? But one of those colors is used a second time. So there's 3 choices for which color is used twice. Okay, am I going to pick the blue to use that twice? Or the green? Or the orange? So that's a challenge. Okay, so 3 choices there. And then where can these colors go? Right? One of these colors is special because I'm using it twice. So if the sort of duplicated color, I might call it, is used opposite itself, there's really only one way to do that. So on one way to place the duplicate color opposite itself, right? Sort of diagonal-wise. Okay. And then it doesn't really matter which one's green and which one's orange, because if I were to rotate the whole thing, I would get the same picture the other way, the same way of splitting things up. And remember, one of the things we learn in 1.4 is rotational symmetry. Oops, I've got the wrong coloring there. So these are the same thing, because they're just around a circle. George rotates his piece of paper, and they look the same. So he hasn't really colored these differently. Okay, so we can ignore that if you're wondering about that. But what if he places the color that is duplicated beside itself? Right? Well, then we actually do get 2 different ways to color. So same color side by side. That's the other possible way. It's the other possible case. So it's this. So the same color is diagonal, or, different case, it's side by side. And then what do we have? Well, there's two choices. Okay? I've got two colors left over. I have to choose which one goes on, let's say, if I'm the blue, if I'm sort of at the blue circle, which one goes on my left? Is it the green or is it the orange? Okay. Two choices. So which other color is on the left? Okay. So let's see what we've got here. One way for that case, or there's two ways for this case, so those get added up. So once I've chosen which color is duplicated, I've got three ways to actually color things in. So first I choose which color is used twice, and then I choose which way to color things in. Multiplication rule says multiply those together, 9. And now we can add everything together. 3 ways plus 12 ways plus 9 ways. And you add those up and you get 24. 24 different ways for George to be using his anything but red. So that's, again, not necessarily the fastest or best way to do it, but that's how I would break it down into various cases there. Okay. Now, that was just C. Let's look at D for a moment. How many ways can a child who isn't George color the circle? Okay. So this is someone who now has the availability of all 4 colors. Now, maybe we could go back and sort of do this same sort of work. Okay. Break it down by cases, but maybe we think, is there a better way to do this? Is there a sort of a faster way? Okay. Maybe not breaking things down with cases. So if I'm a child who's got access to, say, all 4 colors, I could sort of color anything I want, however I want, but I have to be a little careful. If I color red and red and blue and blue, I want to be sure that that is considered separate. Like that's considered only one way if I accidentally color red here and red here, blue here and blue here. So we have to watch things out, or watch out for things. And so, is there really a clean, slick way to do it? I can't really see it, so we might have to just do more of this sort of case-based work. And fortunately, we've already done a bunch of this sort of thought experiment. Okay. So we already know from George, if we have, so by part C, George, if we have 3 colors at most, because George could use 1, or he could use 2, or he could use 3, then there were 24 ways to color. So what's the difference between George and any other child? Well, George could only use 3. Another child could use 4, and that's the only thing we're missing. Okay, so we'll use these 24 plus the number of ways to use exactly 4 colors, because other children can use the red. Okay. So when we view this sort of as a, okay, well, George was sort of easing us into the problem, now let's make it a little harder, we might say, okay, well, if I'm going to use exactly 4 colors, and there's only 4 spots on the circle, I have to use each color once. Right? So no choice of what colors, I've got to use all 4 colors. So 4 colors to pick, or well, 4 colors to place, but I don't have anything to pick. I've got to use all 4. Right? And so it's just a question of, well, how do I shade things in around a circle? Right? And this is where circle permutations, again, can come back into play. This idea of rotational symmetry affecting how we color things. There's 4 different colors to place around a circle. What have we learned? 4 minus 1 factorial, or 3 factorial, or 6. So you might for a moment think, aha, the answer must be 24 plus 6, 30. Right? But is that entirely accurate? We used our knowledge of what George did. But George had to have 3 colors. Okay? But which 3 colors did he necessarily have access to? Right? So if we go back and reconsider George's problem, if he used exactly 1 color, we're saying he had 3 ways to pick that color. But a kid who isn't George would have had 4 ways. A kid who isn't George would have had 4 ways to pick which of the 3 colors he uses here. Pick which one you're not going to use. Pick the red in your situation. Okay? And a kid who's using exactly 2 wouldn't have 3 ways to pick his 2 colors. He would have 6 ways to pick 2 of the 4 colors. And that's going to change things a little bit as well. Okay? So one kid who has access to all 4 colors is going to have 4 ways to use 1 color. And instead of 3 times 4, he's going to have 6 times 4, 24 ways to use exactly 2 colors. He's going to have 4 times 3 ways to use exactly 3 colors. And finally, he's going to have this 6 ways to use exactly 4 colors. Okay, so the George is the right idea, but we don't want to use exactly the number of ways George did things. So 4 plus 6 times 4 plus 4 times 3 plus our 3 factorial. 4 plus 24 plus 12 plus 6. And we see we get 46 ways